All right, welcome again, Trinity Classical Academy, to a video with math in it. This is your host, Magister Bourgeois. Once again, I'm recording this very late at night, and so please have grace if I make a flub of some variety. So we're starting with number 1. I'm just going to move my way through. You have permission to fast forward to ones that you want to see. Actually, you know what I should do is I'll post the answer key. So if you're watching this and you don't already know that the answer key is posted, I will post it. And then you can just look at your answers and grade your own. And then if you want to see the explanation, you can watch this video right here that you're watching right now. So we'll do that. Sounds great. Righty-ho. Number 1, a bag is filled with colored golf balls. Let A be the event of randomly selecting a yellow golf ball from the bag. Give the meaning of the complement of A. So with this meaning, a complement of A, if A is picking a yellow golf ball, then A complement would be picking a non-yellow golf ball, because the complement is the opposite, right? I wish this worked better. There we go. Picking a technically A prime, or the complement of A, is the event of picking a non-yellow golf ball. That's that. That is just simply the definition of the complement. It's any event that does not satisfy the event. So the event is picking a yellow golf ball, then picking a golf ball that is not yellow is the complement. So between those two, there's a 100% chance of either A or the complement of A happening. Just basic definitions. Number 2. A month is chosen at random. Let X represent the event of choosing a month that will with only 30 days. Let Y represent the event of choosing a month that has 4 letters. Are events X and Y mutually exclusive? Explain. Well, let's see. There's the old maxim. I suppose for this kind you'd have to know which months have 30 days or not. 30 days has September, April, June, and November. That's the little rhyme I learned. September, April, June, November. So there's event X that says 30 days. And then there's event Y, which is 4-letter month. And we see they would be mutually exclusive if it was impossible that any month would satisfy both of those conditions. However, June has 30 days and satisfies both conditions, so they are not mutually exclusive. It has 30 days and also 4 letters. Number 3, this is simple mathematical rule recall. Number 3 says, what is the value of the sum of all relative frequencies in an event? So given that, we know that even if you forgot what all those were talking about, what has Mr. Bourgeois always been talking about with regard to the sum must always equal something? The relative frequencies are given as generally a decimal. So like 0.21 might be one, and then 0.46 might be another one, and then 0.33 might be another one. And then you'd see, aha, these all add up to 1.0. So the answer is 1. They all add up to 1, always. The relative frequencies add up to 1. If you put 100% on the checkpoint, I would consider that to be okay. A spinner. A spinner has 8 values as shown in the diagram. What is the probability of the spinner landing on the number 8? Well, looking at that spinner, it looks to be divided into 8 equal parts, and we're assuming it's a fair spinner, even though it does look kind of wonky, I don't know. So it says give the answer as a percent. So since calculators are allowed on this one, you could take 1, divide it by 8, and you should get 0.15, which equals 15%. And as I'm looking at the, I'm looking at the wrong one. I was like, that doesn't seem right. 0.15 isn't all right. I was looking at the wrong part of the answer key. Like I said, late at night. It is. It should be 12.5%. 1 divided by 8 equals 0.125 in decimal form, which is 12.5%. That should have been number 4. Yeah, the late night's gonna get me. You guys be like, Mr. Bourgeois, can I recommend a correction? Yeah, I already got you. Number 5, 2 coins. They are tossed. Let H be the event that at least one coin lands on heads. List all of the favorable outcomes of H. Well, what are the ways that coin 1 could land? It could land heads, and then coin 2 could land heads. We could get heads and then tails. We could get tails and then heads. And we could get tails and then tails. These are the four outcomes. So let H be the outcome that one of them is a head, at least one. These are them. This is not one of them. So there are 3 outcomes: heads, heads, tails, heads, and heads, heads, tails, heads, heads, tails. Those are the outcomes. That is your answer. Number 6. A fair number cube is rolled. I think they mean a die. 6-sided die. Let W be the event of rolling a prime number. Why do they call it a fair number cube? That is so bizarre. Let W be the event of rolling a prime number. List all the favorable outcomes of W prime, the complement of W. So the complement of W. If W is a prime number, then the outcomes favorable to the complement of W would be all of the non-prime numbers on the face of a die. So let me just start by listing all the die values. And now let's identify which ones are prime. And we're going to use Galaxy Pen to zap them out of existence. 2 is a prime number. 3 is a prime number. And 5 is a prime number. So the events that are favorable to our outcome are 1, 4, and 6. There you go. Because event W are the prime numbers, and they say list the favorable outcomes to the complement of W. You list the non-prime numbers. Tricky, those guys. Number 7. Johan randomly selects a word from the following list. Had, ever, than, me, dry, head, red, sly. Let E represent the event of selecting a word with the letter E. And let H represent the event of selecting a word with the letter H. Draw a Venn diagram to represent the information. We have to draw the Venn diagram. So first we start with a rectangle, which contains all possible outcomes. And then we need event H. If it has an H in it, it goes in there. If it has an E in it, it goes in there. I'm gonna start by writing the words and then drawing the circles around them, because I think it's easier to draw circles that way. So I'm gonna look for the words that satisfy both events first. I'm gonna stick them in the middle. Had, ever, than, me, dry, head. Okay, there's one. Head, red, sly. Okay, no others have both in them. So I know that this one's going to be encirculated by all of the circles. Next, all the words that have an H. So there's had, ever, than, me, dry, head. I already got. Red, that's not one of them. All right, so those are it. Those are the H. I've got H right here. Woo! Next, we're going to have the ones that contain an E. So there's ever. There's me. And there's head, and there's red. And then we need to write the words that satisfy neither event. Dry and Sly. And that is our Venn diagram. It looks like a couple of beans. One bean that might be eating another. This bean over here is trying to eat the other bean. Like I said, very tired. It's late at night. However, even though I'm tired, I'm still having a really good time with you guys. I enjoy your company, your fake company. I'm imagining that you're here, and it fills my heart with some kind of a warmth. Number 8. 3 randomly chosen colors produced the following experimental probability results. Ooh, we have to deduce. It's simplicity itself, my dear Watson. We have to deduce the missing value. What is the value of P? Blue P. Color. So we have over here, we have red, we have blue, and we have green. Red equals 0.34. This is the unknown we're trying to find, and this is 0.51. Go Team Green, my favorite color. So we know that all of these have to add up to equal 1.0. So we take 1.0 and we subtract the other values. So these two added up. We'll use rainbow pen because it's magical like unicorns or something. Rainbow pen. So we're looking at, we're gonna, subtract 0.85, yes? Oh, my computer doesn't like it when I get close to the edge of the screen right there. It tries to shut things down. There we go. I've got this song called if you don't know who these guys are, they're a Christian, like really hard rap rock group coming up. And I don't know why I said coming up, but they're really hard, like dance electronica. This is your answer, by the way. That's the value of P right there. How many? That's the relative frequency of blue, or the probability of blue coming up in the random test. But they do like intense dance music, and they're Christian, and so they're not going to swear, and so it's kind of nice. But chainsaw is in my head right now. Bow to my knees and break it like a chain, crank it like a chainsaw. It's just pretty intense. I thought I'd listen to it before I did this video, so I could stay awake for it. I'm still pretty tired. Bow to the knees and crank it like a chainsaw. Chainsaw. All right, number 9. There are 3 red counters, 4 green counters, and 5 yellow counters in a bag. A counter is drawn from the bag at random. What is the probability of drawing a green counter? Well, to figure out this probability, we're going to need to know the number of green counters. It's 4. Divide that by the number of total counters, which would be 12. So the probability is 1/3. Checking the answer key, making sure I'm not smoking crack. I am not smoking crack, according to the answer key, or at least that means I'm not wrong. Just because you're wrong doesn't mean you're smoking crack, but in my case it might be. You never can tell. Number B, what is the probability of drawing a counter that is not red? Well, there are 9 not red counters in that bag, which is 3/4. Bow to my knees and crank it like a chainsaw. Those are your answers. You take because I'm supposed to be explaining how the problem gets did, you're supposed to take the number that satisfies the event divided by the total number of outcomes. So because there are 12 different tokens, that means there are 12 outcomes. And because there are 9 non-red counters, that goes in the numerator, gives us the probability. Weeky, 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 week, week, week. I'm sailing away, set an open course to the Virgin Seas. There are 3 red cards placed face down on the table, numbered 5, 6, and 7, respectively. You randomly arrange these cards to form a 3-digit number. List all the possible outcomes of the sample space. So we have 5, we have 6, and we have 7. I hate writing 5s with this stupid thing. So we could do 5, 6, and 7. We could also do 5, 7, 6. Those are all the different ways that we can arrange a 3-digit number that starts with a 5. Now let's do the 6s. 6, 5, 7, or 6, 7, 5. Now let's do the 7s. I think I'll stay here. 7, 6, 5, and 7, 5, 6. These are all of the possible outcomes of the sample space. Yep, that's all 6 of them. Pretty cool, y'all. Coolio. It's been spending most our lives living in a gangster's paradise. What is the probability that the 3-digit number is an odd number? Well, let's take a look at what we did over here. I'm going to use my highlighter. How many odd numbers did we come up with? We're just going to look at the last digit, right? 1, 2, 3, 4. 4 out of 6 are odd, which makes sense because 2 out of 3 of the digits are odd. So stands to reason that there should be a 2/3 chance of a random number being an odd number. Let's do C. C. What is the probability that the 3-digit number is divisible by 3? Now, with numbers divisible by 3, it actually does not matter in what order you arrange the digits. So let's get a different color. How about this one? No, that one. Which numbers are divisible by 3? Let's see. If any of them is divisible by 3, they must all be divisible by 3 because you add the digits up, and if you come up with a divisible number by 3, then it's divisible by 3. Arranging the order that we add them does not change the order, right? I am like getting parched and I don't have water near me. I might have to carry this computer over to a sink where I fill it up with water and then drink the water while you wait and listen to me. Anyway, let's see. Are 5, 6, and 7, do they add up to a 3-digit number? So 5 plus 6 is 11, plus 7 is 18. 18 is divisible by 3, so guess what? 6 out of 6 numbers are divisible by 3. So there's a 100% chance that one of these random numbers is divisible by 3. How about that water now? I'm going to move my computer. We're going to go get me a water while the video still records because I do not have the capability of pausing with this particular app that I'm using. Wiggy, 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 wiggy. Gotta turn the page anyway for numero 11. Happy Cinco de Mayo for yesterday, right? In case you celebrate Mexican independence, which I don't, because I'm not Mexican, so. And also, how independent is anyone really, right? Tough to say. Water. I've heard people say that a virus is not an organism, like the coronavirus. I think the distinction is rather arbitrary. I've talked to an epidemiologist and another, I can't remember who the other person was, some kind of a medical professional person. One of them said, yes, it should be considered an organism, and the other one said, no, it should not be considered an organism because it does not have DNA, it has RNA. Some actually do have DNA instead of RNA. But I feel like still that's an arbitrary distinction that makes no sense. Number 11, in an experiment, my ADHD seems to be firing when I'm late at night. In an experiment, a number cube is rolled 500 times. Number cube, what in the crap? Just call it a die, for crying out loud. It's rolled 500 times, and each time the value on the top face is recorded. It's called rolling a die. We rolled a die 500 times. The results of the experiment are summarized in the probability distribution table below. How many times did the number 6 appear? Okay, so for this we have to, the probability is also a relative frequency. It just means how many times out of 100 did it go. And so we look at the chart. I'm not going to redraw the whole chart, but we see the number 6 over here, and we see 0.12 underneath it. So that means that 12% of the time a 6 was rolled. So we take 12% of 500 should yield us the answer. Pulling out my calculator. 500 times 0.12 equals 60. The answer should be 60 times. Checking the answer key. That is the case. All right. Bow to my knees and crank it like a chainsaw. 60. Woohoo! Number B. What is the probability of rolling an even value if you roll the number cube one more time? Number cube. My goodness, that's like, what is that like? Calling a die a number cube? It's like calling a billiard ball, I don't know, pool table spheres. It's just so weird. Football, pigskin, I don't know. So rolling an even number. So what we're going to do is, guys, we're just going to take all the even numbers on this chart and we're going to add them together. And that's really all you got to do. So the even numbers are 2, 4, and 6. So 2 has a probability of 0.14. 4 has a probability of 0.15. This is 2. This is 4. And then 6 we already established was 0.12. Right? We add those together and we get 29, 31, 41? 41%, 0.41? That is the answer. There we go, number 12. Bibbidi bobbidi, bibbidi bobbidi, bibbidi bobbidi boo. The types of yogurt flavors chosen by 80 people at a party are summarized below. Dang straight, chocolate gets 20. Wait, macadamia? That's a yogurt? Whatever. I mean, I probably would try it because I'd be curious what macadamia yogurt was like, but I'm not a big fan of the flavor of macadamia. It's all right, but it's not chocolate or raspberry. I'd probably take raspberry and chocolate and mix them together. Complete the table by finding the relative frequency. Okay, so to find the relative frequency, we take each number and divide it by 80. So 6 divided by 80 is for vanilla. Sad vanilla. So plain. We're fine with vanilla, but we wouldn't pick it in a party. So 6 divided by 80 is 0.75. 0.075, of course. And then you fill it out. So the purpose of this video is to show you how. You take each number and divide it by the total, and you get your answer. That is the relative frequency. It's relative, it's a frequency. 6 is the absolute frequency of vanilla, right? So this is like the frequency, the observed frequency. The relative frequency compares it to everything else. That's what makes it relative. It's compared to all of its, brothers and sisters. It's relatives. It's actually compared to out of 100. Or out of 1. For every 1, I don't know. It's a relative frequency. If it's a percentage, it's out of 100. If it's a decimal, it's out of 1. So that all of them added together equals 1. So number B. So that's how you do it. Fill out the rest of the table yourself. You have the answer key. What is the probability that the next person in the party will choose macadamia flavored yogurt? Give your answer as a percent. It's pretty high probability. I mean, so we got 30 out of 80. 30 out of 80, which equals, 37.5%. So using this as our guide, any random person is 37.5% likely to pick for their one solitary flavor of yogurt macadamia. Although chocolate macadamia raspberry would blow my mind. I would probably go insane. You would not want to see me at a party. You might want to see me at a party. You just wouldn't want to be too close to me at a party if I had that kind of yogurt flavor happening in my mouth. I might get violent. could be crazy, you guys. Present the relative frequencies in a bar graph. All right, bar graph. You know what? I'm actually not going to do this one because you're going to have the answer key and you can look at the bar graph yourself. Maybe I'll give you some pointers on how to draw a good bar graph. A good bar graph should have, you would use a bar graph and not a histogram because these are categorical data points, vanilla, chocolate, strawberry. There's nothing that's like you can't do a number line, right, where there's like, oh, here's 3, and here's 4, and then here's, 3.5. You can't have chocolate point strawberry. You can't, like, categories are not on a continuum. They are like discrete. They are discrete values. So flavors of yogurt are discrete values, not, I can't remember the other thing that it's called, not discrete. Moving on, number 13. In a certain town, at a certain place, 40% of certain residents have a certain pet, and 60% of the residents have at least one green house plant. Among those who have a green house plant, 30% of them also have a pet. Okay, so number 8, draw a Venn diagram. This can be tricky. So we have a certain town. They say 30 of them have a green house plant and also a pet. So we're going to have 30% of, not 30% of the total, but 30% of the, I almost just made the mistake that probably many of you did. 30% of greenhouse plant owners, I'm just going to call them plant owners, 30% of plant owners have pets. So let's just say that there are 100 residents of this town. It's, I don't know, Broken Bow, Nebraska, or someplace small. So 100 people. So that means that there are 60 people, since 60% of them, there are 60 people who own a plant. Of those, 30% have a pet. So we're going to take this and we're going to multiply it by 0.3. And we're going to use our calculator because we can. That's going to be 18 people. 18 people have both a plant and a pet. So be very, very careful about how you read the data that they give you. They say among those who have a greenhouse plant, 30% have a pet. So 30% of the plant owners is 18%. So that goes in the middle. So these are the plant people. And then these are the pet people. Good thing they both start with a P, otherwise this would be easy. But it's not easy, it's fun. So if 40% are in the pet circle, we have to subtract the 18 so we don't count it twice. We don't want to count these people twice in the pet circle. So 40% minus 18 is 22. 22% of people, so 22% have a pet but not a plant. And then we know 60 is the number here, so 60 minus the 18 that we already counted once would be 32? 42. Math and stuff, it's late. And then how many people don't own a pet or a plant? I hope they have a book or something because, man. 18% own neither book nor plant, neither pet nor plant. So let's make sure all these numbers add up to 100. 18 plus 22 is 40, and then 18 plus 42 is 60. So these numbers add up to 100%. there you have it. I hope that was clear how that was done. So we can't just straight up put a 40 here because the whole circle adds up to 40. All of the pet owners are 40%. 22 plus 18 is 40. So 22% own only a pet. Let me highlight this. 22% own a pet but not a plant. Is that green? I should have used that for the plant owner. Here. I think this is green. Let me see. Green highlighter. Boom. There it is. Okay. What color should we make pets? Let's make them... Struggling, guys. These colors. Black. Pet owners get dark gray. So pet owners are 22%. Sorry if this is killing the point. And then we have 18% that own both. And now we'll use orange for neither. So really there are 4 types of people described here. People that own pets but not plants, plants but not pets, both plants and pets, and neither pet nor plant. So we've counted all people in exactly one category, and they add up to 100%. Boom shakalaka. Shakalaka laka 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 laka. All right. Oh snap! I should have left that up for letter B. B. If one of the residents is selected at random, that would have been nice if I left that up. Can I do this? Boom! Control Z to the rescue. Let's zoom it out. So if one resident is selected at random, what is the probability that the person has a pet but not a plant? 22%. Boom, we nailed it. No, go away. So 22%, that's B. I do believe so. Let me check. What? Why would you give that as a fraction? Am I looking at the right one? Okay, whatever. So this is B sub I. Why don't they just make it B and C? B sub I? Stupid. I guess it's Roman numeral 1, because the next one is B sub II, which would be Roman numeral 2. B sub 2. What is the probability that a person has neither a plant nor a greenhouse plant? We already established that's 18%. But the answer key gives them in fractions, which I think is really a bad idea. It's not how I would do it, which means it's not the best way. That was very prideful of me. But it was a joke. You knew it was a joke, right? I'm only joking. 20 house flowers were randomly selected from a garden. The heights of the flowers were measured in centimeters and recorded below. Look at all those centimeters. Complete the frequency table. Good luck, you guys. I realize this is a timed checkpoint, but this is time consuming. So any flower that is between 70 and 80 centimeters, you count them, and then you write down the number. You just straight up have to go across this table and count. So there's 1, 2, 3, 4, 4 that are meet the first criteria. Now, if I cheat and look at the answer key, I will see that they are all 4. There are 4 in each category. All right. Complete the frequency table. Well, it's going to look like 1/5 in all of these. Right? They should all be the same because they are all, the same. Then it says, construct a probability distribution table. Is it a uniform probability model? So you construct the probability distribution table, and the answer is yes, it's uniform. Why? Because they're all the same. That's what uniform means. They're all the same. So guys, I hope that answers all of your questions. I hope that satiates your curiosities. And I hope you have a lovely rest of your school year. 7th graders, you're about to become 8th graders. What? I'm super stoked. All right, good night, y'all. I'm going to bed.